Alright, so this is an explanation video on generators specifically. So we've spoken about motors before, and generators, there's two main types that I want to talk about today. There are AC generators and DC generators. And as the name suggests, an AC generator will generate AC voltage and a DC generator will generate DC voltage. And funnily enough, in terms of their actual structure, a DC generator uses or looks almost identical to its counterpart DC motor, except for a couple specific and very minor differences. So right now what I'm drawing looks a lot like a motor structure. So if you see here, you've still got the spring-loaded carbon brushes, your split ring commutator, but instead of a power source, what you have is a load. So normally, in a motor, you would have a battery here, but instead of that, you switch it out with a load. What is a load? So a load is something that uses electrical energy, right? Because what a generator does is it converts kinetic energy to electrical energy, right? It converts kinetic energy to electrical energy. Motors do the opposite. Motors go from electrical energy to kinetic energy. So generators go from kinetic energy to electrical energy. So that electrical energy is used up by some sort of load that you've connected to the system. You can typically represent it as some resistance. And then that kinetic energy comes from a physical torque, applied torque, usually in the form of, like, for instance, someone cranking this rotor, right? You can see this is a little handle here. I'm turning this rotor manually, or this rotor / armature manually, and this is generating the EMF within the system. Okay, so let me name a couple of these things. So this is a rotor / armature. This is the resistance, or the load. This is the stator, no different. Now, how does this electricity actually get generated? Well, it's actually via something called Faraday-Lenz's law. So let's say you decide to crank this generator, right? So you decide to turn it like so, right? You decide to turn it like so. And it ends up in a new position. It ends up in a position, ends up in a new position like this. Right? So in that situation, you now have increasing magnetic flux through this loop to the right. So there is an increasing flux through this loop, and it's to the right, because that's the magnetic field there, right? So in response, by Faraday-Lenz's law, this loop will want to produce an opposing magnetic field, and therefore an EMF, whose current produces a magnetic field that opposes the original change in flux. So the EMF, or the opposing magnetic field generated, is going to be opposite to this. And in order to do that, it needs to produce an EMF that is in this direction. And you can verify that with right-hand rule. Yep. So the EMF that's generated is going to be in this direction. But this time, unlike in a previous DC motor, there is no supply EMF, right? Because this is going from kinetic energy to electrical energy. So as a result, you're going from just kinetic energy, which is you cranking the motor, has created a change in flux that induces an EMF, and this EMF drives a current, and that is the electrical energy produced by the generator. And what I've just described here is a application of Faraday-Lenz's law, right? So this EMF here drives a current, and this is the generated electricity. Now, this split ring commutator will reverse the direction of the generated EMF every half period. And keep in mind, every time this rotor moves past the vertical position, the EMF will switch in direction. So as a result, the net of these two interactions, the EMF switching every half period because it switches at the vertical, and the split ring commutator, which will reverse the direction of connection between the internal and external circuit every half period, ends up with the final voltage being produced as a DC voltage. So you can think that through to make sure you understand that. But the final voltage produced is a DC voltage, and that is then conferred to the load. And you can make that similar argument for an AC motor as well, just as easily. The components that make up an AC motor is almost identical to the components that make up the AC generator. The only difference is that that's a horrible drawing, one will have a battery source or a supply source, whereas the other will be connected to some form of load instead and have an ability to deliver torque to the system in order to crank the rotor. So likewise, you can see in this generator, there is load attached, and then there is some sort of crank that allows you to turn this rotor manually. But everything else stays largely the same. Cool. So I've introduced the generators now. So what does this actual output look like? If you were to draw a graph of the output, the DC output would look much as you'd expect. It would look something like this. And then the AC output, again, would look much as you expect, which is something like this. So that is due to the fact that one of them has a split ring commutator and one of them has a slip ring commutator. Okay, so the next thing I want to talk about is something called back torque. Back torque. So if you recall, in motors, there is something called back EMF, right? So the motor effect is what, and how about I talk about that first? So in motors, the motor effect is what drives the actual motor forward. And then the back EMF is what, or due to Faraday Lenz's law, is what opposes the supply voltage and causes the back EMF, right? And this is the supply torque. However, and I'll draw this here, motors. However, in generators, the opposite phenomenon is happening. In generators, the Faraday Lenz's law is actually the supply voltage, is supplying the generated electricity, right? Or in other words, it's producing the generated electricity. However, the motor effect will now produce something called back torque, and that is what we will speak about now. So you can see that motor effect and Faraday Lenz's law have different purposes in a motor and in a generator. So let's speak about back torque. Back torque is what happens when you have an EMF, and let's copy this diagram up here to make it a bit easier. So you can see here that we have this generated electricity, which is great. But as soon as we have this generated electricity, there is now current that flows within the circuit. And we know that current is going to be in the same direction as the EMF. So let's put that in, EMF and current. However, what you realize is that as you're trying to turn the generator this way to produce that yellow current, what do you notice about motor effect acting on this current that you've just generated? Well, if you use your right-hand palm rule, you'll quickly figure out that the force on this yellow current is actually downwards. And it is acting against or producing a torque that is against the torque that you are using to turn the actual rotor. And that torque produced by this motor effect within a generator, that is what we call back torque. Back torque is the torque due to motor effect on your generated current, or on your generated current inside the generator. And importantly, it always acts against the applied torque. So however you try to turn the motor, your back torque will always act against it. And as you probably have already guessed, this is very much due to the conservation of energy. And you can verify this using the same method I taught you before, called proof by contradiction. So you can assume that back torque actually acts along the applied torque and see where you get with that. You'll find that there is infinite energy, and therefore by contradiction, back torque must act against the applied torque. Cool. So the last thing I want to emphasize is that motors and generators aren't all that different. You can see here already that they share some of very similar properties in the sense that they're both governed by motor effect and Faraday Lenz's law, except those laws will surface themselves in concepts in different ways. So in motors, motor effect will be a supply torque and will help the motor along, and the Faraday Lenz's law will produce a back EMF that sort of opposes the supply EMF. And then in generators, the Faraday Lenz's law will produce the voltage we want, and then the back torque will act against us, right, due to the motor effect. What happens if we look at a graph of the net EMF versus the speed of the motor, right? So, interestingly enough, we know that the current is equal to supply minus back EMF divided by R. So this V here, just to clarify, is the speed of rotation. So we know that as the speed of the rotation goes up, right, we know that the back EMF should go up. And this is because the flux change happens a lot quicker as you speed up. So we know that. And so we also know that if the back EMF increases, this guy here, then the current is going to decrease. Or in other words, the net EMF, which is this here, the net EMF, if the back EMF goes up, the net EMF goes down, right? So let's imagine that decrease, the decrease of the net EMF, is linear for the purpose of making this a bit simpler. So you start off with some maximum amount of net EMF, and that represents the supply EMF. Why? Because your maximum amount of net EMF is when your back EMF is 0, right? And you're not turning at all. As you go down, this is what happens as you speed up, right? You speed up, your back EMF goes up, your net EMF goes down. So interestingly enough, when you hit this point here, this is what we call max speed, right? Assuming you have a frictionless motor, max speed is achieved when your back EMF is actually equal to your supply EMF and your current draw is 0. What do you think happens after you pass this point? Well, if it's max speed, you need some external torque in order to get faster, and you enter a region that we've now learned is called generators. So below this graph here is generators. Why do I say generators? Because if you increase past the maximum speed, you are actually applying torque to the system, and you've effectively reversed the direction of the net EMF. And reversing the direction of the net EMF means that you are now, instead of drawing current, you are supplying current into an external load. So this side is motors, and then the other side is generators. So what I want to emphasize here is that this is on a continuum. It is not two sort of very, very distinct types of physics objects. These motors and generators are on a continuum. They share the very similar physics concepts, and hopefully this has been informative in helping you understand how generators are related to motors. Generators, remember, kinetic energy to electrical. Motors are electrical energy to kinetic. Two sides of the same coin. Cool.